Hi. I wanted to say near the very beginning of lecture 27A what to expect for the rest of the course, but forgot until about 5 or 10 minutes into the lecture, and I talked about it then. Let me say it here at the start of lecture 27B as well. So where are we in our main textbook about differential equations? We are just finishing chapter 3. In fact, in lecture 27A, I started chapter 4. So in the lecture A's, from now on, we're hoping to end around lecture 35 or 36. I'm still going to continue with this content, chapters 4, 5, and the first 3 sections, hopefully, of chapter 6, which gets into nonlinear systems and something called Laplace transforms. In the lecture B's, and it's a lecture B and C for 27, I'm hoping it's just lecture B's from now on instead of lecture C's as well. I'm going to continue to linger in chapter 3 of this book, but apply the linear algebra content to that, the more advanced linear algebra content. That will include lecture 27B right now, which is very similar to lecture 26C, which was our main purpose for the course, to understand linear systems of differential equations in terms of a change of variables. But now it's going to be for a very special example called a symmetric matrix, which will be what's called orthogonally diagonalizable. Lecture 27C is pretty theoretical as well. It's based on something called Jordan canonical forms, which again is kind of a difficult topic, but if we think about it in a special case of a 2x2, it's not too bad, okay? We won't do the fully general topic there. And as we continue through to lectures 35 and 36, we'll continue talking about essentially focusing on applying the linear algebra ideas to differential equations and difference equations. All right, let's get into the content of lecture 27B. So this is a second change of variables example. Our first was in lecture 26C, where we ended up looking at a saddle point. This time we're going to end up looking at a source. The origin is going to be a source. Let's consider an example whose coefficient matrix is called a symmetric matrix. What does that mean? The definition of a symmetric matrix is that its transpose equals itself. Very special kind of matrix. This is the example. Now this example is symmetric more than in just this way. If you take the transpose of this, it certainly does equal itself. Exchange the rows and columns. However, I don't really have to have the numbers in the main diagonal equal to each other to make it be a symmetric matrix. As long as those numbers on the off diagonal, the 1 and the 1 there, are the same in a 2x2 case, the matrix will be symmetric. The transpose will equal the same as the matrix itself. So the first row of this matrix is the same as the first column, and the second row of this matrix is the same as the second column. The transpose equals itself, even if these two numbers are not the same. I chose them to be the same because it does make the math work out a little simpler, but it didn't have to. Okay? This theory will apply even to the example I just erased, but the numbers don't work out quite as nice, and irrational numbers often become involved. All right, let's go ahead and think through what we know about such a situation. We can certainly try to solve the initial value problem by thinking about the characteristic polynomial and the eigenvalues. Remember, the characteristic polynomial is lambda squared minus the trace times lambda plus the determinant. The trace is the sum of the numbers in the main diagonal. 2 plus 2 is 4, so I get a minus 4 lambda there. The determinant is 2 times 2 is 4, minus 1 times 1 is 1, 4 minus 1 is 3, so I get a 3 there. And I've made it nice. This is easy to factor. Lambda minus 1 times lambda minus 3. Set that equal to 0 and solve for the eigenvalues. You get a first eigenvalue of 1 and a second of 3. 2 real positive distinct eigenvalues. This will be diagonalizable. And this origin will be a source because those are 2 positive real eigenvalues. It'll be a non-spiral source, in fact. What are the corresponding eigenvectors? Here are the details. Lambda 1 is 1. You'll get this homogeneous equation, system to solve, which you can reduce row echelon form to that, which can give you this eigenvector. I purposely chose to do it a little differently than I usually do here. This line would say x plus y is 0, and so therefore x would be negative y. And you'd think of y as a free variable, and you might pick y to be 1, and therefore x would be negative 1. So it would be more common to pick negative 1 there and positive 1 there. But it turned out for some other reasons that this worked nicer, so I chose y to be -1 and then x is +1. For the other eigenvector, corresponding to the other eigenvalue, 3, you get 1, 1. Yes, v1 and v2 are not multiples of each other, they are linearly independent. But they're more than just linearly independent, and here's where the special fact about the symmetric matrix comes in. They have a dot product that equals 0. What do we know about dot products when they equal 0? We know that means the vectors are perpendicular. Orthogonal is the more official word. And it is good to use the more official word, orthogonal, because for one thing, this will apply to higher dimensions that we can't visualize. For another thing, the orthogonal vectors do apply when one of them is the 0 vector, and the 0 vector is just a dot, so how can it be perpendicular to the other one? And for another thing, when we generalize dot products to something called inner products, in, I don't know, maybe three lectures from now, 4, something like that, there will be a similar concept related to inner products being 0, inner products of functions being 0, functions somehow being perpendicular to each other, which does harken back to lecture 27a when I talked about sets of functions being parallel to each other. It's actually no accident. Any symmetric matrix is going to have, well, linearly independent eigenvectors that are orthogonal to each other, if you look at the linearly independent ones. Don't look at multiples of a given eigenvector. This ends up being very important, actually. It's got a lot of applications, and we'll try to tease out those applications as we go here, one of which is in this lecture. It's part of the spectral theorem that this is true. Spectral theorem sounds like it's an important theorem, and it is. Okay? And it has nothing to do with spectroscopy in physics, as far as I know at least. So it's called the spectral theorem. Choosing an orthonormal basis of vectors, basis vectors for the change of variables or change of coordinates. What in the world is that? Remember that once we've found the eigenvalues and eigenvectors, if we want to diagonalize A, we want to create a P matrix, a change of coordinates matrix really, whose columns are the linearly independent eigenvectors of A. And I could do that with the other vectors that I had in the other slide, v1 and v2, but it's going to be helpful to normalize v1 and v2. Way back, lecture 4, 5, 6, something like that, I did talk about normalizing vectors, finding unit vectors, vectors of length 1, in the same direction as the given vector. Unit vectors, that's what's called vector normalization. It's not the same thing as a normal vector to a plane, which is orthogonal to the plane. It's not the same idea. It's unfortunate that we use the word normal again. This will result in what's called a set of orthonormal basis vectors. Vectors that are orthogonal to each other and normalized in the sense of having length 1. How do you do this? Just got to find the magnitudes of those vectors, their lengths, and multiply these vectors by 1 over their lengths. And they are non-zero vectors on the previous slide, so we can do that. We won't be dividing by 0, but you can write it as division by the lengths of those vectors. Why is this helpful? Because what's going to happen, almost like magic, is P inverse is going to be easy to compute. In fact, it's going to be the transpose of P. P transpose. P inverse will equal P transpose when you do this, when you make the vectors orthonormal. If you don't normalize them, then it doesn't quite work. So that's why it's nice to do this. And that's a good thing, especially in the higher dimensional case, because once you're above 2 by 2, finding inverses can be a lot of work. Even for a computer, once you go high enough, I don't know, above 10 by 10, computer programs can bog down in finding inverses then, although maybe not so much these days. By the way, this is a -1 here. This is P inverse. It's very handy. Taking the transpose is easy. Just swap the rows and columns. In the present example, it's not such a big deal because it's easy to find inverses of 2 by 2 matrices, but it does work here still. Here are the normalized vectors. You might say, unfortunately, we involve square roots that we can't get rid of. Yeah, it's a small price to pay, actually. Okay? The lengths of each of v1 and v2 are square root of 2. So multiply each of these vectors by 1 over the square root of 2. And you get these two column vectors that you can put in your matrix P. This first one is the first column, and the second one is the second column. And P inverse does equal P transpose. If you swap the columns here, make the first column of P the first row of P transpose, and the second column of P the second row of P transpose. I'm not going to take the time to check it, but you should check that this is the inverse of P. You could multiply P and P inverse. You'd see you get the identity matrix. You could use the shortcut formula to compute the inverse of P. Its determinant equals 1. And you get P inverse. What's the benefit of this? This has the benefit that the linear transformation that maps an arbitrary vector, call it u, to P times u, this feels like lecture 26c, where y was equal to P times u, the vector boldface y. Just another notation for the mapping. I could have written T of u equals P times u. Ends up preserving distances, both in 2 dimensions and higher dimensional problems, and even areas in 2 dimensions. When you look at images of sets, the areas are preserved. It's called an isometry. In fact, for this example, it ends up being a rigid rotation. And it was because that's nice and simple that I chose the V1 to have the minus sign in the second spot here instead of the first spot. To make this be a rigid rotation. In fact, if you think about it, you can check this, the angle ends up being negative 45 degrees. Which reminds me, I forgot at the end of lecture A to look at the Mathematica. Guess we'll look at that in the end of lecture B for both parts of A and B, if I don't forget. Note the determinant of P equals 1. We have talked about how the determinant of a matrix in 2 dimensions tells you how it affects the areas of the images. For a given set with area equal to, just pretend it's 10, the area of its image is going to be, would be 10 times the absolute value of the determinant in general. Our determinant's 1, so it's not going to affect the area. It's an isometry. Forgot to mention here, a matrix P such that the inverse is the transpose is called an orthogonal matrix, which is kind of mysterious. Why wouldn't you call it an orthonormal matrix? We're stuck with the terminology. I will use that term in future lectures, so that is something to remember. A matrix whose inverse is transposed, not just in 2 dimensions, but higher dimensions, is called an orthogonal matrix. By the way, if this is true, P must necessarily be a square matrix, because otherwise you can't even talk about the inverse. Continuing, what was our goal here? Our goal is to relate this to change of variables and diagonalization and thinking about the phase plane and maybe changing coordinates, changing the axes. That's our goal. We can also relate it to the matrix exponential, though we don't have to do that. I think it's worthwhile to do it to remind ourselves about the matrix exponential. It's a nice way to think about solutions. You can check that. This is true. The original matrix A is P times D times P inverse, but P inverse is P transpose, so that's P times D times P transpose. Do this product. Go ahead and take 3 minutes to do it. You will see that you get 2, 1, 1, 2, the original matrix A. Therefore, we've seen this before. If we look at the matrix exponential of T times A, which is going to be our unique solution of an initial value problem, dy dt equals a times y, where the initial condition is y sub 0, is e to the ta times y0. That's the beautiful generalization that I've been talking about. E to the ta is the same as e to the t times, by this previous line, P times D times P inverse, or in this case, P transpose, because P is an orthogonal matrix. And then that turns out to equal this. I did justify that intuitively in terms of Taylor series already. Plug those matrices in, do the multiplication, you're going to end up with this. So this matrix evidently must be e to the ta, where A is this matrix. And we can check that in Mathematica. Now relating it to change of variables. U is the new variable, y is the old variable. Though when you initially think about change of variables, you have the old variable in terms of the new. Y is p times u, pu, easy to remember. A little weird, I mean, wouldn't you want to solve for the new variable, u, in terms of y? Sure, you can just take the inverse, which in this case is the transpose, times y. So these two things are equivalent to each other. If this is true, that's true, and vice versa. This is u in terms of y, which allows us to write the differential equation for u in lecture 26, was it B or C? I forgot. C, I think. I did that in terms of the components initially. Yeah, it was C. And then I did it in vector matrix form. Let's just do it in vector matrix form. Du dt, you can check all this work, where again we use P transpose here because it equals P inverse. In lecture 26C, we always use P inverse because P was not an orthogonal matrix in lecture 26C. Here in lecture 27B, it is an orthogonal matrix, so we can write the P transposes in place of P inverse. Go ahead and check. You get D times U, you get a diagonal matrix times U. So in terms of U coordinates, the differential equation involves a matrix that's diagonal, yay, matrix exponential, and solutions are easy to find. In terms of little u and little v, it's a completely decoupled system. Again, the solutions are easy to find. But we would want to ultimately translate back to y. We are interested in y as a function of t. We already know the answer, but it would be good to do the translation back. I did that in lecture 26C. I'm not going to do it here. I'm going to focus on the visualization for the rest of this lecture. Visualizing the change of coordinates. These graphs I'm about to show you are analogous to the graphs at the end of lecture 26C. We're going to look at the phase plane for the original system. We actually write it up here. Your y dt was a times y, where a was the symmetric matrix. The no-clines, that means the x no-cline is where dx dt is 0. That's going to be where the first row, when you multiply times x and y, is 0. 2x plus y is 0, which means y is negative 2x, aligned through the origin with a slope of negative 2. And the y no-cline comes from the dy dt equation. Dy dt would be x plus 2y. So x plus 2y is 0. Y is going to be negative 1/2 x. So both of these no-clines happen to have negative slopes. The reflections of each other across a line through the origin of slope negative 1. You can use those to help you draw it if you were trying to do it by hand. Again, the eigenvalues are 1 and 3. They are positive, so the origin is a source. You could draw the eigenvectors in here. I do. In orange, I've drawn the eigenspaces, which are parallel to the eigenvectors. Let's see. The eigenvalues, again, were negative 1, or excuse me, positive 1 and 3. And the eigenvectors that we wrote down v1 to be 1, negative 1, and v2 to be 1, 1. In this picture, v1, let's make it black, it's 1, negative 1. Scale is fairly big. Actually, in my next picture, I make the scale smaller. v1 is a vector about like this, maybe even smaller. It starts at the origin. I made the origin big black dot to emphasize its equilibrium point. There's v1, v2, be about like this. Those vectors are perpendicular, orthogonal to each other. We already knew that. The dot product of v1 and v2 is 0. The orange lines are perpendicular. They looked like they were perpendicular in lecture 26C, but they actually were not quite perpendicular. If you go back to 26C, you'll see that. Here for the symmetric matrix, basis of eigenvectors is orthogonal. You can also normalize them to make them orthonormal. These eigenspaces for those eigenvalues have to be perpendicular to each other. These orange axes, new axes, are perpendicular to each other. yeah, this one corresponds to the positive eigenvalue, because you see solutions moving away. Well, okay, they're both positive, sorry. They're both positive. The one parallel to that one corresponds to the eigenvalue 1. The one parallel to this one corresponds to the eigenvalue 3. Subtle point, remember we said the eigenvalue that's closer to 0 when these are real is what solutions are tangent to. If it were a sink, it would be as t goes to plus infinity. Here, because it's a source, most solutions are tangent to this eigenvector as t goes to minus infinity. As you can see, if you follow one of these curves backwards, it's tangent to this orange line rather than the other orange line. Yeah, got the noclines in there as well. X nocline in brown, pink, Y nocline in pink. Looks good. In terms of graph paper, skewed graph paper, it looks like this. Here I zoomed in. So negative 20 to 20 in both directions. I went negative 5 to 5. And these squares, these are really squares, actually. Based on the normalized versions of these things, for example, the vector starting at the origin going to this point has components 1 over square root of 2, negative 1 over square root of 2. That was the normalized version of V1. And notice this next grid line starts parallel to this axis and starts at the tip of that normalized version of V1. This vector here going from the origin to that point is the normalized version of V2. Divide V2 by its length. It's got components 1 over square root of 2 for the first and also 1 over square root of 2 for the second. And they are orthogonal still. That's the slanted coordinates, the skewed coordinates in this case. It's with respect to those coordinates that the system is simple, the matrix is diagonal, completely decoupled. And that makes sense intuitively if you take your head and turn it sideways and focus on the orange grid and the blue solution curves. And it looks like something you would get with such a simple system. du dt equals u and dv dt equals 3v based on the eigenvalues. You would ignore the noclines in there. The noclines are no longer noclines for that rotated system. Right, the pink and brown, based on the rotated system with your head at a 45-degree angle like this, would not be noclines for that system. So you ignore those, but focus, you can still focus on the grid, and you can still focus on the blue solution curves made in Mathematica with stream plot. All right, let's look at Mathematica. I do want to do quickly through lecture 27A as well. If you didn't watch it, you may want to go back and watch it here. We solved the second order forced harmonic oscillator equation at the start of lecture 27A where the right-hand side forcing function was 7e to the negative 4t. This confirms we get the same answer. That is the same answer we got. We can also confirm it this way. When we plug it into the left-hand side linear operator, we get 7e to the negative 4t. And the initial conditions are satisfied. And I can plot those functions. There's, well, yeah, I forgot to plot this one actually. I did plot the other one in the PowerPoint. This is the one where the forcing function is 7e to the negative 4t. The mass, the motion's not that complicated. It starts from rest 1 meter to the right of equilibrium. And essentially it heads toward equilibrium without oscillating, even with the forcing function. Essentially because the forcing function becomes so small so fast. With the other one, the polynomial growth, this confirms the original solution. Another confirmation. And the graph, this was the one where we said the spring breaks. For here, lecture 27B. Here's the eigensystem. And by the way, in a minute or two, I'm going to show you something very important that I hope you're stuck with me for here in terms of visualizing the change of variables. Here's P, its determinant is 1. It does match a negative 45-degree rotation matrix. rotation matrix, negative 45 degree. These two things match. It is geometrically a rotation clockwise by 45 degrees around the origin. And there's the matrix D. I couldn't call it capital D because Mathematica reserves that for the differentiation operator. PD, P transpose is the original matrix A. And you can, for example, compute the matrix exponential in these various ways. These are all equal to each other. These two are equal to each other, at least after you multiply by the initial condition. You can also use the solve value and get the same answer, and we can make our phase plane, there it is, and a rotated one, well, with a grid. All right, here we are now to the animations that are going to be still important to listen to carefully here. This is something I showed you in 26C. One way to imagine the change of coordinates is to actually rotate the axes. The red axis that started out parallel on the x-axis rotates by 45 degrees to the u-axis. The blue line that started on the y-axis rotates 45 degrees to the v-axis. That's one way to visualize it. However, this way of visualizing it is extra tricky, so to speak, because the change of variables, remember, is y equals p times u, which is equivalent to u equals p inverse times y. But focusing on that part, which is really what is acting on it here, I'm multiplying by p, it gets confusing. Because p is supposed to convert the new coordinates to the old. And it seems like in this picture we're converting the old coordinates to the new, as these axes rotate rigidly. Well, it's because you're thinking about it in the wrong way, if you think that. The key thing is that a vector, for example, like this vector here, let's do it again. I guess it doesn't let me draw it when it's Mathematica. It's only in the PowerPoint. Okay, that's why. The vector that goes from the origin to this line here, right there, at that point, that was our v1 vector, our normalized 1 square root of 2, negative 1 square root of 2. In terms of uv coordinates, it's 1 unit along the u-axis and 0 units along the v. Its uv coordinates are 1, 0. When I multiply p times 1, 0, I get the y coordinates at that point, the xy coordinates, based on the original coordinate system, the old coordinates, which are 1 over root 2, negative 1 over root 2. It gets confusing, okay? U and v, it's 1, 0. X and y, it's 1 over root 2, negative 1 over root 2. So even though that converts u to y, it's confusing because you can still think of it as a rotation from the x and y axes to v axis, u and v axis. Probably a less confusing way to think about it is actually to do this, and this is my final point. To actually imagine two different coordinate systems based on two different planes. Well, are there two different planes? Pretend there are two different planes here. A plane over here and a plane over there, and maybe this one's in front of the other ones, so they aren't actually the same plane. Over here the axes are labeled u and v. Over here the axes are labeled x and y. The system in uv coordinates, du dt was a diagonal matrix times u, looks like this, nice and simple. In fact, the u-note line is the v-axis, and the v-note line is the u-axis. I didn't put a dot in there for the equilibrium at the origin, I should have. But the other one's rotated. How should I imagine the transformation, u getting mapped to p times u, which is y? What I'm doing here is I'm imagining the transformation applying to the sets as this thing moves. In other words, I'm thinking about mapping the original set on the left to the new set on the right, sort of angle by angle. As I let the angle change to say here, what this is telling me is this sector of the original disk gets mapped to this sector of the new disk. And I continue rotating. This half sector of the original disk gets mapped to this half sector of the new disk. Excuse me. Whoa, sorry about that. I got saliva stuck in my throat, and it was very difficult to get out of that. But I'm okay now, I think. Let me just comment that this emphasizes initially that this positive u-axis gets mapped to this positive axis there. As theta continues to change, like to get to right about there, that's emphasizing the positive v-axis over here is getting mapped to this positive slanted v-axis over here, etc. That perhaps, once you understand it, is a less confusing way to think about changing coordinates. Thanks for watching. I am okay. I'm doing okay. Thanks for watching.